We will begin with a simple string, stretched under tension. The main component we're interested in here is the string itself, stretched between two rigid points under tension. We all know from our intuition and experience that if we decrease the tension, the pitch goes down. And if we shorten the string, the pitch goes up. Similarly, the longer the string, the lower the pitch. And the higher the tension means higher pitch. The equation for the ideal string under tension is shown here. This is called the wave equation in one dimension, which indicates that the acceleration in the y direction, up and down, is a function of the curvature, or how curved or kinked the string is, at each point along the string in the x direction. As with Fourier's theorem, we won't prove this equation, or even solve it directly at each point along the string to make sound. But for interest, we can actually solve this equation directly at each point along a virtual string, as the simulation here shows. In this code, we approximate the curvature by looking at the difference between slopes to the left and right of each point along the string. And we use the calculated acceleration as a result to add to the velocity at that point. Adding velocities yield position. Let's run this code. We've loaded our string up with an initial triangle-shaped string in the center. And if we tell it to run, the curvature, which was the point where the string kinked at the top of the triangle, is where the wave propagates outward from. That's exactly in keeping with our equation, which says that acceleration is proportional to curvature. We can load this string with other shapes as well, like we can pluck it near the end and watch it run from there. Or we can load it with a pulse in the center, like striking it with a hammer. We can do all of that calculation at an animation rate of 30 frames per second or so, but it would take a lot of computation to do that at audio rate, because we'd have to compute and update at least 44,100 times per second for every point along the string, and the number of points along the string depends on the length. The longer the string, lower the note, the more computation would be required. Fortunately, it turns out that there are easier ways to simulate this physical vibrating system. Remember that Joseph Fourier told us that we could make any waveform by adding sine waves together. So also we can make any shape, like the shape of a plucked string, the very same way by adding sine waves together. As we showed before, we can add the individual harmonics together to build up a sawtooth shape, which would be similar to plucking the string towards the edge. This is called the Fourier model, or Fourier solution to the plucked string. Any shape we can dream up to pluck the string, usually just a ramp with a peak at some plucking point, we can make by adding sines together at the right amplitudes. So for example, here is plucking it at the center with a pulse. Here is plucking it in a triangle shape, which we did before. Here would be plucking it in a ramp shape towards the edge. It's wiggly because we're only adding a finite number of sine waves together to build this shape up. We can even pluck it with a square shape if we wanted to, which would be like picking this string up on both ends and letting it go. All of these we can solve by using Fourier's theorem. This is just a sum of sine waves, and so when I tell the system to run, it's just advancing those sine waves in time. Note that we're getting exactly the same solution that we did by doing the laborious point-by-point calculation of curvature and acceleration in the literal physical solution, but here we're just doing it by calculating and adding together a few sine waves. In a real non-ideal string, there are losses, friction and heat inside the string from bending and stretching, and air friction as the string moves and cuts the air. These cause the string sine modes to die away exponentially, just like an individual mass spring damper for each harmonic. The losses are greater at higher frequencies, so the decay is faster for higher harmonics. Let's look at that in Chuck code. Note that in this code, we're just doing a harmonic additive synthesis with a slightly different decay rate for each mode. The modes are set with amplitudes equal to 1 over the harmonic number to make a sawtooth shape, like we're plucking the string on the edge. And we're using this to set the decay time of each harmonic. Let's hear what that sounds like. If we don't need to know the actual shape of the string while we're synthesizing it, we don't need to keep track of the spatial harmonics, just these harmonics in time. So it's a physically motivated solution in synthesis, but not as physical as if we kept track of the spatial harmonics and string shape as well.